A slow underground movement passed through the forests and steaming terraces of Yellowstone National Park, so subtle that most tourists on the boardwalks barely noticed it. At first, it seemed to be only a passing tremor, something occasional in the park's vast volcanic basin. This time, however, the vibrations did not stop. They intensified, repeated themselves, and within a few hours the network of sensors spread across the region began sending alerts to scientific teams that had monitored the system for decades. Yellowstone, once relatively quiet, was awakening from a long period of relative stability. Far beneath the caldera, an immense reservoir of molten rock, dormant for thousands of years, began to stir again. Instruments recorded a significant increase in pressure, accompanied by swarms of small, shallow and persistent earthquakes along ancient geological faults. These tremors, unusual in frequency, depth and synchronization, indicated that magma was gradually moving toward higher levels of the crust. Heat increased, previously trapped gases escaped more rapidly, and the ground began to rise in irregular and progressive pulses. Satellite data revealed growing deformation, with parts of the terrain rising several centimeters within a few days, an extraordinary rate for geological processes normally measured in millimeters per year. Hot springs became more intense and unstable. Mud pools began to bubble with renewed energy, while geysers erupted with greater frequency and vigor. Chemical alterations changed colors and patterns, reflecting shifts in the mineral composition and temperature of underground fluids. Scientists observed that hotter and more fluid magma migrated from deep reservoirs to shallower regions, connecting areas that had previously been isolated. This integration significantly increased the energetic and explosive potential of the volcanic system. Experts knew that Yellowstone did not need to produce a supereruption to generate severe consequences. Even a moderate eruption could transform entire landscapes, alter ecosystems, interrupt air routes, and influence global climate patterns. Gas emissions became critical indicators. Rising carbon dioxide suggested the ascent of new magmatic material, while changes in rare isotopes indicated deep fractures releasing ancient gases that had remained trapped in the crust for extremely long periods. Seismic swarms continued around the caldera, including harmonic tremors directly associated with magma movement. Sensors recorded a steady rise in underground temperature, and groundwater began to boil at shallower depths, releasing steam with greater intensity. Water levels in springs and natural reservoirs fluctuated abruptly, reflecting changes in internal pressure. Despite this, the surface remained apparently calm. Tourists walked, photographers captured landscapes, and animals moved across the fields without fully perceiving the magnitude of the forces operating beneath them. The awakening brought significant ecological implications. Ground uplift could alter river courses, modify lake levels, and affect underground water sources. Plants sensitive to heat began to experience thermal stress, while microorganisms adapted to specific conditions faced abrupt changes. Animals altered migratory and behavioral patterns, moving away from warmer and more unstable areas, demonstrating early sensitivity to subterranean changes. Geologically, new fractures could open pathways for future eruptions in regions that had been inactive for tens of thousands of years. Hydrothermal explosions, caused by superheated steam, could form craters suddenly and violently. On a global scale, emissions of gases and ash could affect air quality, disrupt air transport, and influence agriculture. Atmospheric currents could disperse particles over vast distances, altering temperatures and precipitation patterns in distant regions. The greatest challenge faced by scientists was the unpredictability of the system. Magma could stabilize temporarily or continue ascending, increasing the risk. Thermal sensors detected heat spreading laterally through the crust. Trees near geothermal areas showed signs of prolonged stress, and the soil became progressively hotter. At the same time, electromagnetic changes indicated interaction between magma and deep minerals, altering the electrical conductivity of the crust and revealing complex internal reorganizations. Chemical analyses of the water revealed an increase in the concentration of dissolved minerals, including silica and other elements associated with magmatic activity. Microscopic particles of volcanic glass detected in the air indicated interaction between magma and groundwater at great depths. The caldera exhibited complex deformations, with central uplift accompanied by peripheral subsidence, indicating an internal redistribution of pressure. Satellites detected thermal emissions expanding horizontally, forming a vast subterranean dome of heat. Deep sounds and low-frequency vibrations were recorded, reflecting the movement of fluids and transforming rocks. These changes indicated that the volcanic system was entering a more active phase, even though no imminent eruption was yet expected. This awakening carried profound scientific implications. It challenged traditional models that considered long periods of dormancy to be stable. It also offered a rare opportunity to observe volcanic processes in real time, allowing significant advances in understanding the internal dynamics of supervolcanoes and improving monitoring and forecasting systems. More than an isolated event, it was a progressive and multifaceted transformation. Yellowstone revealed the immense geological power accumulated over millions of years. This awakening served as a reminder that Earth is a dynamic system in constant evolution, whose forces operate independently of human presence. The volcano had not yet erupted, but its reactivation demonstrated that enormous energies were in motion. When a geological giant awakens, its consequences can extend beyond regional borders and influence natural systems on a continental and even global scale. As the signals continued to evolve, researchers intensified continuous monitoring, integrating seismic, thermal, and geochemical data into increasingly precise three-dimensional models. Each new reading helped reveal details of the system's internal architecture, exposing channels, pockets, and zones of weakness previously unknown. What emerged was not merely a possible eruptive precursor, but a dynamic portrait of a living, pulsating system in constant reorganization, reminding us that even periods of apparent quiet conceal deep and transformative processes. Thank you for watching. While you are here, do not forget to like the video and subscribe to the channel. Click on one of the recommended videos on the screen for more incredible information. See you there.